Hi, hi Benito. We are just getting started. There are few more people is missing. We'll just find it out and then maybe just give it a minute or so. We'll start. Yeah.
Yeah, no worries.
Thanks.
Can you hear me fine?
Yeah, sure.
Okay, perfect. Yeah.
All right. Let's get started with the afternoon session where we'll continue with the theme of FRB surveys and instrumentation. The first talk is going to be by Benito Marcote, where we'll hear about localizing FRBs at the highest angular resolution. Benito, I'll give you a 25-minute warning maybe.
Okay, thank you very much. Okay, thank you, everyone. I hope you had a good lunch. First, I would like to say sorry for not being there with you. I was really hoping to be there, but yeah, we had to cancel the flight at the very last minute. So I hope that next time we can make it there. So thanks for the invitation anyways, and for allowing me to give this talk. I will continue with a talk focused on instrumentation and how it's the application to FRBs. So in this talk, I will focus on all the results that has been done with the European VLBA network and how and why basically we can localize, why it's important to localize fast radio bursts to the millisecond level, to the very high angular resolution. So basically we'll give 3 parts in the talk. I will introduce quickly fast reverse because I know that most of you have been already on the school, and then the previous talks has already touched the topic. But then I wanted as motivation of why we actually want to observe FRBs at the very highest resolution, and why only through that basically we can understand what are the local environments where FRBs are produced. And by that, basically, we can actually narrow down what are the different formation channels that can produce FRBs. And then the second part, I will go through the results. And then basically my points there is like, thanks to these observations, the ones that I will summarize and the ones that we are still doing, basically what we are seeing is that different environments like FRBs are produced and are localized in completely different environments. And we see and we believe that actually there are different formation channels that can be led into FRB objects. And something that we are seeing, and then still something to be proven, is if some of the most extreme population of FRBs maybe have some consistent host or environments. And then this is kind of the motivation of this talk. So again, I don't need to explain what an FRB is. You've already seen a lot during the past week and now. The two main points that I want to say is like, even if the field is really recent, like the first FRB was discovered only in 2007, we already know thousands of these objects. However, we only know where these FRBs are produced, in which host galaxies or which local environments, for a handful, only tens of them. So even if we know already a really large population of FRBs, we only have really very detailed information on a very few of these objects. Furthermore, we know that even across the entire population, only a very small fraction, like roughly 4% of the ones that we know, seems to produce more than one burst. So we know that the vast majority of the FRB population is what we call non-repeating. So they only display one burst and nothing else after that. And then a really tiny fraction of them exhibits multiple bursts with time. Not periodic, but then we saw more than one. We still don't completely know why this is happening, if they are two different populations. We believe like probably it's still the same population, just different conditions, different lifetimes, but again, this is still something under discussion. However, we've discovered so many FRBs in such a few years because the rates are really high. So there are roughly 10 to 3, 10 to 4 FRBs detectable per sky and per day, given the current sensitivities of radio antennas, which means that there are some volumetric rates of 10 to 5 FRBs per gigaparsec, cubic gigaparsec per year. And this is much higher than any other rate as compared to the supernovae or GRBs. So that means that FRBs is truly a different population of objects. And the fact that we haven't localized most of them with enough precision led to really huge variety of different sources to explain what FRBs can be. At the very beginning, we could still even contemplate things that were happening in our galaxy. And that had the particularity that over time, until recently, until Chime started discovering hundreds of FRBs every few months, we had actually more possible theories to explain FRBs than actual FRBs that we discovered. And this is because we discovered a lot of FRBs, but then we didn't know where they were produced, which conditions were leading to this emission. And this is one of the focus where we started, and we saw the motivation of conducting very high resolution observations. We really need to know where FRBs are produced in order to understand them. In any case, despite all these theories, the ones that soon win a lot of potential was everything that was related to young neutron star or magnetars. And actually, this was really strengthened by the discovery of FRB-like emission in a galactic magnetar that was already known beforehand. And this is the only case where we've seen such an emission in an object within our galaxy. was already mentioned before, but then this is a kind of isolated magnetar. So actually this put it in context, this kind of emissions, and then it led into strengthen this kind of theories. The interesting part of this particular event is that it was not only detected at the radio wavelengths, but also on X-rays. And actually, there were some X-ray bursts at the similar times as the radio ones. And this was actually predicted by many theories, and still many theories predict that at least many of the FRBs should have a counterpart at higher energies, either optical, X-rays, or even further to gamma rays. However, from this one, what we saw is that maybe we are just not sensitive enough to detect the X-ray emission for most of them, because this was happening in our galaxy. If you go to a really far galaxy, we are just not sensitive enough to detect the X-ray counterpart. But again, this is something that I think we should always keep in mind on the FRB contest, that even if the entire field is dominated from the radio domain, because it's where we detected all the emission, it's something that has implications outside the radio domain. And actually it's something that is really interesting to search for different wavelengths and having simultaneous observations outside the radio domain. But this is not the only interesting part on FRBs. We study these sources basically because they have a lot of potential. The fact that they emit just a fraction of a second, just around 1 millisecond, and they travel such a long distances, means that that light carries a lot of information that has implications on many different fields. So a part of course, the interest of trying to understand what objects can produce FRBs, the other particularities is that by studying these sources, we can actually trace back a lot of properties from the universe, from the intergalactic medium, from the reionization history, and even in fundamental physics, because we are just measuring really fraction of times traveling like above high redshifts. And this is quite of the most interesting part of FRBs, and that's why there are many people interested on this. But again, we have quite a large population already, but we don't understand where they are produced. And if we really want to understand what can produce FRBs, we really need to understand where they are formed, where they are located, and what conditions are around it. So that's why observations like with the European VLBI network is really relevant, because for most of the single dishes, we have a really poor resolution. There are thousands of possible counterparts associated to FRBs. The fact that there is no extra emission or afterglows after each FRB means that we cannot actually narrow down and identify any other transient source associated to the FRBs. And as you can see here, just moving from single dish, even from Parkes to Arecibo, VLA, equivalent to GMRT, it narrows down, but then we go to really distant galaxies, we really need a much better resolution that is only possible with VLBI. And by that, we can trace not only the host galaxies, but actually also the local environments within that galaxy. And that's what actually leads us to understand what are the progenitors. So we only by studying the local environments of FRBs, we can actually understand how and where these events are produced. And that's why we've been observing it with the European VLBI network, which is a network of antennas, mainly in Europe, but also with antennas in Asia, Africa, even America. And then we observe at centimeter wavelengths in general, and then we can reach resolutions of the order of 1 millisecond, which means that we can achieve resolutions on the parsec scale for redshift between 0.1 and 1. And it's really good that, for example, the GMRT can actually now participate in observations within the EVN. And recently, since last month, actually, even Marcote, which means that we will actually boost a lot the sensitivity of these arrays and actually the resolution or the precision that we can achieve in these localizations. So far, we haven't observed yet any FRB with EVN plus UMRT, but then we are really waiting for it because that will improve a lot the accuracy that we can reach in our images. And then during all these years, we've been conducting regular observations with the EVN. All the results that we will put here are in the context of the PRECISE and AstroFlash groups projects that I'm part of. And then we've been basically targeting repeating fast radio bursts because are the only ones that we don't know when they will happen, but we know where roughly they will happen. And then the precision basically coming from chime for most of them, it's good enough to actually observe them with our dishes. And then from there, we can actually localize it, doesn't matter where within the primary beam, even if once we correlate, we have a really tiny field of view, but then actually we can reconstruct any image within the primary beam of these dishes. So what can we do with VLBI observations on the field of FRBs? Well, we can, as I said, localize it to millisecond level. That's what we did with the first ever localized fast radio burst, 2012-1102. We found that this FRB was localized into a low metallicity star-forming dwarf galaxy. And actually, the FRBs were coming from really inside the star-forming region, a prominent star-forming region there, as you can see here. Even more interestingly, these FRBs were consistent in position with a persistent radio emission, really compact, as you can see on the left image. That's the persistent emission. It's less than 0.7 parsec in size, and that's really constraining because if you can think on different possible scenarios, we assume like this is a young neutron star, you can think that this is the supernova Ramanujan or the pulsar wind nebula, but comparing with the galactic cases like the Crab Nebula, it's already much bigger than this source. So we can put strong constraints on either the nature and the age of these systems. And actually, this looks like a quite interesting case because we know that, for example, long GRBs are produced in this kind of systems in low metallicity star-forming regions of dwarf galaxies. So this was the first FRB that was ever localized, and then we thought that it could be the pattern, but as we saw later, this was kind of an exception until recently. So we didn't know if there is a possible connection on GRBs forming really young magnetars and producing such an emission. But as I said, this was kind of the exception, but in the last years, we've been seeing a few FRBs that are called kind of twins of this FRB because they are in similar contexts. So we localize another FRB, like 190512, that is also in a dwarf galaxy. It's also inside a star-forming region, and it's also associated to a persistent radio counterpart. Just because this source is farther away, our limits on the size of this object are a bit poorer, but still, we know that it's a really compact source. It's less than 9 parsecs. Which means that it's already putting some constraints on the models that can explain this emission. And even more recently, this year, we just submitted another localization on another FRB, 190417, which also is associated to a persistent radio source, also really compact on millisecond scales, and also in a dwarf galaxy. And these were kind of almost the only objects, the only FRBs that has been found in dwarf galaxies. And these ones are actually the ones that seems to have either a higher activity or a much larger Faraday rotation measure, which means that it seems like these FRBs are actually the most extreme population of FRBs. Do we expect the most extreme FRBs associated to persistent radio counterparts? maybe yes, maybe no. This is still an open question, but maybe we are actually narrow down what's the scenario that can explain these sources and why we have this persistent emission. There is, of course, and then we can see here, this is just a plot between the galaxy, the host galaxy magnitudes, and different redshifts for different FRBs. All the green boxes are just standard not repeating or repeating FRBs. And then the stars are the ones that I just mentioned, the most extreme FRBs that are actually associated to persistent radio counterparts. So you can see here that these ones are actually in the low end of the host galaxies. And we only have 3/4 of these systems, so we still cannot trace any statistics, any proper statistics here. But maybe this is telling us that the most extreme FRBs are actually located in these low metallicity dwarf galaxies, and probably associated to some either young nebula associated to them, or because they are in a more extreme scenario. There is only another case, two cases where the FRBs are also associated to dwarf or are found in dwarf galaxies, but without any persistent emission. And one of them, 190208 on the left, is actually the dwarf galaxy is even way fainter, way smaller than any other one by 1 order of magnitude. And recently, we just submitted another one where the FRB is actually in a satellite dwarf galaxy from another companion or main galaxy. But what this is telling us is actually that not only having a sensitive radio surveys to detect FRBs are critical, but also having really deep optical emission, optical telescope, optical images. Because as you can see here on the right, the dwarf galaxy where the FRB was localized, it's really faint in the optical. And actually in the previous case, in this one, the galaxy was not even detected in most of the images that we had. So you really need deep optical surveys in order to find the host galaxies in some of these FRBs. But once you have that, and if we really have millisecond resolution, we can actually put, as I said before, as you saw, really steep, strong constraints on the sizes. And this is the way to actually try to explain what these objects are. We don't know if there is the same object producing the FRBs, or it's just some object that is collocated with it. But due to this compactness, we can actually try to narrow down both the edges and the nature of these systems. So for example, this is a particular case where we actually, thanks to these observations, we can see and we can really limit the possible parameter space under the magnetar with nebulae scenario. And you can see here how we are actually constraining the age of these systems to be really young, which goes consistent with many of the theories that we have. But again, as I said, is the question about if the FRBs and the persistent emission are the same object or different ones in the same, happen to be in the same position, is still open. The two more prominent scenarios is where we have a magnetar with nebula or a superluminous supernovae. And of course, we have the magnetar inside it. So that's why they are collocated. But then, given that we are seeing many of these ones in dwarf galaxies, we know that these systems may have a potential number of intermediate or just almost stellar mass, intermediate mass black holes. So it seems reasonable, and still it's possible that we have a magnetar just orbiting this kind of systems. And the persistent emission comes from the whole system itself. However, this is just a very tiny piece of the whole history on the FRBs that we know, because these are selection of the ones that are in dwarf galaxies. And whereas all these ones can be explained by the similar, at least, scenario, we know that some FRBs are in a completely radical different scenario. So for example, the second FRB that was localized, 1809-16, was found to be in a spiral galaxy similar to the Milky Way, but they're still quite close to a star-forming region, which is kind of a pattern in many of the FRBs. As you can see here, the tiny green dot is where the FRBs are coming from. And the color image is just the optical image from the Hubble. So as you can see here, the FRB is actually outside this star-forming region, which means that under the assumption that this is a really young object, it should have been formed inside the star-forming region. So it requires quite a significant time to travel away from this region. So the only possible to have a young neutron star, or presumably active magnetar here, is that it's located in a binary system. So you may need a companion star that acts actually speeding up and refueling these systems. So this is actually, in addition, the only FRB that seems to have a really clear period of activity. So every 16 days, there is a window of around 4 days where the bursts are produced. And this is really constant and periodic with the time. So we've been observing it for years now. And then we see that this activity is really persistent. So this also goes in favor of this kind of models where the FRB is produced within a binary system, because 16 days seems to be a reasonable orbital period on this kind of systems. And we've been seeing that most of the repeating FRBs, or many of them, are associated to star-forming regions. But we have so far only one exception, which is this FRB, 200120, which was actually localized in a global cluster. So there is nothing really young there. And that's why we believe that there are different formation channels that may lead to FRB emission. This FRB had other particularities, like so far is the ones where we detected the narrowest emission. So far we have subcomponents within a burst that are as narrow as 60 nanoseconds. And here we are just limited by the instrumentation. But then we see that there are different properties in different FRBs. And then I will just start finishing here. One thing that I want to highlight above this is that if you think on FRB searches or FRB detections, you have systems that you don't know when they are happening, but then you need to keep observing. So even with all these detections and results, you can keep in mind that FRBs require a lot of observational efforts. So to put in the context, within the PRECISE project, we've been basically spending thousands of hours. We've been localizing several FRBs, but then if you add the signal, the actual signal from FRBs, it lasts for less than 1 second, which means that FRBs require a lot of observational time in order to produce results. But when you have it and then you detect the FRBs, you can get the precise localizations, as you saw in the previous slides, temporal resolution. And I haven't mentioned in this talk, but also you can get some accurate energy distribution of the burst. And with that, I will just go to the conclusions. FRBs is still a really exciting field, because there is a lot of opening questions. Observations with VLBI are, in our opinion, key to understand the local environments, so to try to narrow down the formation channels that can lead to FRB production. And so far, we've been localizing FRBs on millisecond level. Since this year, CHIME is already localizing almost at the same level on the tens of milliseconds, and other instruments will come forward. But then instruments like the EBN, especially now that it gets in combination with GMRT or even Marcote, we can actually achieve micro Jansky sensitivity and millisecond resolution at the same time. And right now we are going through trying to get more localizations of these FRBs, especially if we can find more FRBs associated to persistent radio sources, because from here we think that we have much information in order to understand how these FRBs are produced, because we can actually study this persistent radio emission and put stronger constraints on it. And with that, thanks everyone for listening.
Thanks for your talk, Benito. Questions for the speaker?
Hi. So if you find more FRBs, more extreme FRBs in dwarf galaxies, the number density of dwarf galaxies is supposed to be huge, right? So ideally you should find more such cases. But that is not what is happening, right? Another thing is, but if even if you are right, then there is a possibility that there are some interlooper dwarf galaxies which are found in other localizations. What is your opinion about it?
That's a very good question. Indeed, if we go to dwarf galaxies, the number would be really huge. Even if, I put the samples and those are the only ones that have been found in dwarf galaxies, if you think that there are hundreds of FRBs localized, this is a really tiny fraction. So we think that the key point here may be the lifetimes on FRBs. That is something that is really poorly constrained, but of course the key point is like how long these FRBs may last on these particular conditions. Just to put one possible scenario, which is not the most promising one, not the only one, it's just one of them. Let's say that, for example, they are associated to just a very young magnet that was produced there. Maybe the lifetimes of this, and this is why we still have the persistent emission there. Maybe the lifetime of this is really short. So that means that even if there are a lot of possible hosts where these FRBs will produce, the number of ones that we can detect are really few of them.
Okay, thanks.
Any more questions?
Thank you. Very interesting talk. Just a comment about this last point. The number density of sources that have persistent emission, so say something like 121102, is absolutely tiny. It's about 1 per gigaparsec cube. So taking that into account, the selection process of going from star formation in a dwarf galaxy to actually having one of those sources is extremely refined. So it's, even if you take into account the fraction of stars that end up as magnetars and the fraction of them that are young enough, let's say tens of years or something like that, to produce a persistent source, even that will be too abundant. You actually need to be more selective than that. So we have to keep in mind all the time that these are very, very rare sources. Those sources that we see as persistent sources, they are intrinsically very rare. And there could be there must be additional selection effects going on between the intrinsic population and what we actually see.
Yeah, exactly. That's, I think, the main point that we structured from here. Like, we know this is a tiny one. It's interesting to study them in detail because it seems to be the most extreme environment. So that's why we are putting special interest on these ones. But indeed, this is a really tiny fraction and really selective fraction of the entire population. And the other one that it's even more goes into the selection and why we don't detect more of them is like, if you think on dwarf galaxies, this is really faint systems. So for many of the FRBs, once they are beyond a redshift 1 or so, it's likely that we will never detect this kind of emission from there. And that actually goes to some of the FRBs that seem to be hostless, actually. But again, this is really a tiny fraction.
Thanks.
Any other questions? Maybe I'll ask one more. Again, on the same thing of like evolving or like increasing population of FRBs with PRS sources in dwarf galaxies. For those particular candidates, can you comment on whether or not their RM or DMs seem to stand out when you compare it with non-repeaters?
Yeah, so the ones that were treated to PRSs in dwarf galaxies are actually the ones that show a really extreme RM. So the two first ones are the only ones that have RMs of 10 to 4, 10 to 5. And then the other one is still like hundreds, which is remarkable. I mean, way less than the previous ones, but it's still much higher than most of the FRBs, the rest of the FRBs that have been localized. And all these ones exhibit variations on DM. So a long time, still some of them, it can be like higher and down. There seems to be trends, but then still we don't see any like clear trend if it goes down with time or like it's just going up and down on different time scales. But indeed, we talk about these ones as the most extreme cases because the RM is way higher than in the other FRBs, which is already telling you that that environment must be more extreme.
I see. Thanks, Benito. If there aren't any other final thoughts or questions, let's just thank our speaker again. Our next talk is also online by Zhaocheng Gong on binary pulsar detection network.
Yeah, let me share my screen. Yeah. Yeah, can you see my screen?
Yes, we can see your slides.
Hi everyone. My name is Zhaocheng, a DPhil student at the University of Oxford. Today I will talk about our project, LeoNet, a binary pulsar detection network. And binary pulsars are extremely valuable in astrophysics, especially for testing general relativity. However, they are also very difficult to detect because in a binary system, the pulsar's orbital motions causes Doppler shift, which spreads the signal's power across multiple Fourier bins in the frequency domain. And this smearing effect makes the traditional detection methods much less effective. And one common approach for binary pulsar detection is FDAS, which is Fourier domain acceleration search. And FDAS uses the matched filtering with hundreds of trails filters to correct for the Doppler shift, assuming the constant acceleration. And this assumption is valid only when the observation time is shorter than about 1/10 of the orbital period. And FDAS can produce an F dot plan to locate the possible pulsars. And on the right, we can see an example of a simulated F dot plan. The bright point in the middle indicates a binary pulsar with an acceleration of 100 and an initial frequency of 500 Hz. So FDAS is accurate, but a little computationally expensive, which limits its use for the real-time detection. And this slide shows the full processing pipeline of the LeoNet. We start from the dispersed time series data. And if the observation time is shorter than 500 seconds, we need to zero patch it to make all samples constant. We picked 500 seconds because it gives a clean Fourier bin size of exactly 0.02 Hz. So it's a fine value, which makes it much easier and more precise to locate where the pulsar signal lies in the frequency domain. Unlike, for example, 600 seconds, which would give a repeating decimal bin size. And yeah, if the observation time changes, the Fourier domain size, Fourier bin size will also change. So we would have to adjust the template resolutions for each time. And padding all data to 500 seconds keeps the frequency resolution fixed and allow a single set of templates for all data with a different observation time. And then we perform the Fourier transform and split the spectrum into blocks of 4,000 points, and each covering about 8 Hz. And the reason is that the full spectrum is huge. Splitting it reduces the input size and the model complexity, and making training more efficient. To avoid losing a feature near the edges, we add some overlap between blocks. Specifically, we add 100 points on both sides of each block using the neighboring values. So signals close to the boundary are not cut off. And during training, since we know the pulsar spin frequency, we select the block containing that frequency as a positive sample and random noise blocks as negative. During inference, since we do not know the pulsar's frequency, so we have to check all the blocks to make sure no signals is missed. And the key part is the template layer convolution. And each template has 201 points, and which corresponds to the setting of Z max value equal to 200 in FDOS. And Z max represents the maximum frequency drift caused by the Doppler shift of the binary pulsar during the observation. So by using these points, we ensure that the Leoness template covers the same frequency drift range as FDOS, allowing fair comparisons while keeping the design consistent. And all templates are learnable, so the network can automatically optimize them for matched filtering. Finally, the model outputs the spin frequency range of the detected binary pulsar candidate. Yeah, and this is a training data construction. Currently, only a small number of binary pulsars have been detected, so real data alone are not enough to train a deep neural network effectively. So we use SIGPROC to generate synthetic data and build a balanced dataset. And the table on the right shows example parameter settings. And this range is based on the value reported in the pulsar catalogs, but we slightly broaden them so the model can also learn from more extreme conditions. And to make the network adaptable to various observation setups, we generate data with observation times from 100 to 500 seconds and sampling time from like 128 microsecond to 1.31 millisecond. And this diversity improves the network robustness and generalizations to the real telescope data. And here is the architecture of the neural network. And it has two main parts, the Doppler shift elimination part and the classification module. So on the left, the real and imaginary parts of the Fourier spectrum are processed by the template layer with 10 learnable templates, and each corresponding to an acceleration up to the max value equal to 200. And after convolution, we take the absolute value to form the FF dot plan. The field modulation block then takes the observation parameters as input and outputs two factors like beta and gamma to scale and shift the features map, allowing the model to adapt dynamically to different observing configurations. And finally, the classification module extracts the features through convolutional layers and outputs the predicted spin frequency range of the pulsar. And here's our training strategy. So during the training, we reduce the weight of samples with very short observation times and large sampling times. Since their signals are usually too weak and may distract the neural network from learning meaningful features. We also use the neural architecture search to automatically determine the optimal number of the templates in the template layers, which is 10. and balancing the performance and the computational efficiency. Because if we have more templates in the template layers, the inference speed will be decreased. So for the inference, we only process data with observation times longer than 200 seconds because short observations rarely contain enough information to recover the binary pulsar features. We also skip the frequency below 100 Hz since our goal is to detect the millisecond pulsars, which lie in the high frequency band. These restrictions reduce the false positive rate and also improve the efficiency. Finally, by combining results from all blocks, the neural network determines the frequency range where the binary pulsar signals is located. And here's some results. So in most observing conditions, the neural network achieves a lower false negative rate than F does. When the observation time is short, for like 200 seconds, F does perform slightly better in some cases. Like when the sampling time equal to 256 microseconds. However, as the observation time increases, the performance of the neural net improves significantly and quickly surpasses F does, showing a strong ability to recover binary pulsar signals when longer observation time are available. And the false positive rate of the neural network is fixed to 0 through the threshold calibration. So these comparisons purely reflect the detection performance. And here's speed. So for FDAS with a sampling time like 128 microseconds and the observation time of 500 seconds, one observation takes like about 18.3 seconds per observation. And in contrast, the LeoNet takes only about 3.9 milliseconds per observation on an NVIDIA A100 GPU using TensorRT. That's more than 4,600 times faster, making the neural network ideal for the real-time and large-scale pulsar servers. But the neural network still has some limitations. Because our neural network mainly focuses on detecting individual harmonics below 1,000 Hz or below the Nyquist frequency. So in most cases, pulsar energy is concentrated in the fundamental frequency. So this design works very well, and that's why we describe the neural network as designed for the fundamental frequency detection. It can also detect a strong second or third harmonic if it falls within 1,000 Hz. However, if the signal energy is distributed among many weak harmonics, the sensitivity becomes lower. And in the future, we plan to incorporate the harmonic summing mechanism using the recurrent neural network or transformers to model the relationship between the fundamental or harmonic or higher harmonic frequencies, improving the sensitivities to the short duty cycle signals while maintaining the LeoNet's faster inference. And to conclude, the neural network provides a faster and effective alternative to the traditional methods like FDAS for the binary pulsar detection. It works reliably across different observation setups and processes data thousands of times faster and make it suitable for the real-time servers. The main limitation is the absence of the harmonic summing, which we plan to address in the future to improve the detection of more complex pulsar signals. And thank you for listening. And yeah, I'm very happy to take any questions.
Thank you very much. Questions for the speaker? Maybe I can ask the first question. So can you please comment more on the specific templates that you're using for searching? So you mentioned that for match filtering, there are certain templates, right? And probably you're injecting in signals into your synthetic data using certain templates. So can you comment on whether they are like some numerical relativity surrogate models or what are they exactly?
So for the synthetic generation, so we we use the SIGPROC to generate the pure noise data as our negative samples, and also we use the SIGPROC, the fake command, to generate like the binary pulsar signals, and we we know the frequency of the spin frequency of the binary pulsars previously, so we just locate the position of the spin frequency in the spectrum. So we pick this as our positive samples, and to build a balanced data set like 10,000 positive and 10,000 negative, and we can say the and for the conditions here, we using 1 hot to represent the sampling time, like 100 represents the 128 microsecond, and 0100 like something like this to represent the 256 microsecond. And if you want to use the sampling time like 150 microseconds to do the inference, we in principle we use the higher level of sampling time to do the inference. Like if you want to use 150 microsecond to do the inference, you need to set the conditions metrics like 256 microseconds. And for the one more thing I want to talk about is we use 100 seconds data to do the training, but we do not inference or evaluate any data with the observation equal to 100 seconds, because we add this low, very faint signal, very weak signal into the neural network, because we want the neural network to have a more robustness when it facing the low signal to noise ratio data. Yeah.
All right. Thank you. I see there's a question online. Ramesh, can you please unmute yourself and ask the question?
Hi, Zhaocheng. I hope you can hear me.
Yeah, I can hear you.
Yeah, so yes, a very interesting approach, and I think a similar sort of, I think maybe similar sort of thing also mentioned probably early on. So you mentioned that one of the shortcomings is mainly it's not sensitive to harmonics, and so my question was, have you been able to test it on some real data yet, or is it like too primitive?
Yeah, we do test some real data, and we only tested like only one real data. But I think in the future we need to test more real data in the future. And if we got the real data, and we can just easily put it in our pipeline to do the test.
Yeah. Okay. Right. No, I mean, I was just curious that even you mentioned that, that the reason why you need injection, because there are not too many sources, but even in the available sample of binary pulsars, there is a pretty good range in terms of their signal strengths and acceleration and pulse shapes. So that's still like quite a good sample to stress test the approach. That's my feeling, but maybe like you will have some more sensible thoughts. Yes.
Yeah.
Thanks.
Thank you.
Are there any more questions?
Yeah, maybe Zhaocheng, just one thing I have, like you say your template is like 200 points long, and you have 10 learnable templates, correct? So I'm just curious to understand that trade-off between them. If you increase your acceleration range, like right now you are going for a 200 bins acceleration correction, correct? If you increase the range, or if you introduce a one more dimension, how you actually going to play with these templates? Are you going to increase the template length, or are you going to increase the learning number of templates? Any kind of thought on this?
I think for the neural network, I think it's do not need to change the length. But if you want to change the frequency drift value to very high, like 800 or something like this, I think it might be you think about to increase the template, the length of the template. But the reason I chose 200 is basically it's kind of trade-off of the overfitting problems and the performance. So for at now we set the target drift value is 200, but the neural network can detect more, like if the data even if the data has a more frequent drift, like and when I also do some tests for the by using FDOS, like to set the Zmax value equal to 500 and do some tests, and some data can be founded by FDOS and also be founded by the neural network. So the neural network has a very nice generalizations for the binary process, even if they have a very high Zmax Z values.
Understand that learnable template is kind of fixed. You are going to change the length of the template.
Yeah, the template can learn it by itself to optimize the parameters and to let the template fit suitable for very high Z values.
Okay. Are there any other questions? I guess since we have time, I'll ask another question. We know that match filtering should give you the optimal performance regardless of SNR of your injection, at least in the scenario of just white noise. So have you tried to benchmark the performance of LeoNet pipeline against the performance of, let's say, match filtering and test whether or not it's SNR dependent? I would assume it is, but I would like to understand what SNRs it would start degrading in terms of its performance.
You mean to do some tests on different signal to noise ratio?
Yeah.
Yeah, we do the test, and even in the low signal to noise ratio part, the performance of both methods, like LeoNet and the FDOS are decreased, but the performance of LeoNet is still higher than the FDOS. So, and even though there are several we can see there are still several signals can only be detected by the FDOS. I think it is basically because the harmonic summing mechanism. So for in the lower, low signal to noise ratio signal, the fundamental or the higher harmonics frequencies, the power is very low. So for the single harmonics is quite low for the LeoNet to classify it as a positive. So I think this is another this decrease of the performance is basically due to the harmonic absence of the harmonic summing mechanism, but the total performance of the LeoNet is still higher than the FDOS.
Oh, gotcha. Thank you so much. I guess we are doing great on time. Let's thank our speaker again.
Yeah.
Our next speaker up is Raghu, who's giving an in-person talk on binary pulsar, on evaluating RFI removal algorithms for single pulse search.
All right. I hope you can hear me. Hi. Hello, everyone. I'm Raghuttam. I am from University of Manchester, doing a PhD there. And today I'll be talking on evaluating RFI algorithms for single pulse search. I'm from V, and want to come up. Some of my teammates are here as well, Kaustav and Prabhu. So we have submitted this paper to RASTI, and it's under review. Hopefully, we'll be publishing it soon. So, yeah, just to give a motivation of what the work is on, etc. So the motivation for the whole experiment was, the observed signal, we hope it's just noise and astronomical source. So it's easy to find the pulse itself, but then there's not the case. So the observed signal will be sum of astronomical source, thermal noise from instrument or other backgrounds, and RFI. So when we search for faint transient signals, the RFI could lead to either very large number of false positives, report inaccurate parameters, and also sometimes like completely obscure the signal, like here you can't see the pulse. Or it can do everything of all of the above, basically. So RFI can be treated at various stages, like right from anywhere in the signal chain by restricting the number of RFI sources, or like any other methods that are talked before, like in incoherent beam subtraction. But then today, we are basically focusing on post-correlation techniques, that's after beam forming the data. So there are already many existing algorithms, such as sum thresholding, or spectral kurtosis filter, or interquartile range mitigation method, or zero-DM match filtering. So all of these focus on different kinds of RFI aspects, and they try to mitigate it. And there are many more. There are many more coming on using machine learning, using all sorts of other statistics, basically. But which one works best? But why does this question come, which one works best? Let's just try and see which one works best, right? But then there are some problems in real-time pipelines that are being deployed now. That includes the real-time pipelines do not give a chance to reprocess the data. So once a run is through and it's gone, so we just have some metadata after that. So you have been listening to all talks this morning, probably even last week. So we don't have chance to reprocess the data. And so for this experiment, we are specifically focusing on simulated data, because the real observational data have many things which are not in our control, like contributions from sky, instrument response, RFI, or probably even pineapple fields right beside the telescopes. So in this, the question becomes the detectability of the pulse that needed to be tested. So hence, we ended up running single pulse searches. Okay. So we have developed a method to evaluate how good any RFI algorithm is, at least to our use cases, and in a controlled environment. So we do this using something called test vectors. So how do we generate test vectors? Test vectors are nothing but the filter bank files. They look something like this. You have time in x-axis and frequency in y. It's basically a heat map with greens and blues showing the intensity. So you can see a faint pulse here, noise. So you have Gaussian noise, and then to that we inject a pulse. A pulse might have many different parameters, and also we have some snippets of RFI. So these RFI here might look really systematic, and there are also a few components that we try to include, such as this, and these are from probably satellite passing across, and then these are broadband, short RFI instances like you get from lightning or something, and we have some narrowband as well. So the dimensionality of the problem is such. So any pulse can have different DMs, different widths, different signal to noise ratios, and an infinite number of RFI instances. So we try to break down everything in terms of how much we can. So we can break down RFIs as periodic narrowband or narrowband constant RFI, and we have periodic broadband and periodic constant, this broadband constant. So we don't consider broadband constant as a different entity right now because we have we try to encapsulate all the characteristics in a constant broadband RFI as short periodic RFIs as well, because that's how our algorithm works. So we generate 3 kinds of test vectors. The first set looks something like this. It has kind of realistic scenarios. And the second set is just pure noise. It don't have any RFI. And the third set would look something like this. It has just broadband RFI. And we have another set which has just narrowband periodic RFI, spread all across, affecting around 25% of a band. So as for RFI mitigation algorithm themselves, we have IQRM and SKF, which are implemented on per channel statistics basis. So it treats every individual channel. It takes statistic measures of them, like in moments, and then also try to flag if they are RFI affected or not. And the second one is ZDMF filtering. It stands for zero DM matched filtering. And it works on an entire block of data. It doesn't mask any particular channels, but then work on a complete TF block, a time frequency block. So just for example, if we pass this filter bank across all the 3 RFI mitigation algorithms, we get something like this. So you see the top one is cleaned using IQRM, bottom one, the middle one is from SKF, and the bottom one using ZDMF. Just to focus a bit more on them, so you have something like this for IQRM and SKF, where you basically flag every few channels depending on where the RFI is. And for ZDMF, you can't get rid of these short instances of RFI which have only spread across few frequency bands. So yeah, continuing the pipeline that we used. So we searched the data for single pulses using a pipeline called Cheetah. It basically redisperses the data and then does something called boxcar filtering that we did last week, and then does clustering and sifting. So for clustering and sifting, please refer to the next talk that's coming up by Shubham. He's going to talk about these techniques. I have used something called Friends of Friends. So yeah, so in order to validate when we pass something through single pulse search pipeline, is that exactly the pulse that we injected or not? We use something called protests if it doesn't find any pulse, basically. So protest is a product testing framework to ensure that the behavior of pipeline is right. So it knows the pulse parameters of every pulse, and then it applies some kind of thresholds based on the pulse parameters and try to see if that's the exact pulse that was injected. So we have example, we have like arrival time, dispersion measure, and width of pulse. So example, something like this would be right because it's de-dispersed at right DM, and this would be wrong. And same with the boxcar filtering. So if the matched boxcar is right or not. So for results, I think exactly I'm on time. For results, so after running 3,360 minutes of data, or like say 20,000 pulses. So we have 3 different sets. So we have 3 different kinds of results. So the set 1, we used IQRM only, IQRM and ZDMF, SKF at ZDMF, so that we have good coverage of broadband and narrowband RFI removal algorithms. And we got something like this. So it might take a while to explain this. So you see the y-axis is DMs and the x-axis is fraction of recovered pulses. So if we inject 6 pulses, we expect 6 pulses back. And this is just the fraction of them. So for in case of say strong RFI, which we have all broadband, narrowband, and periodic RFIs, we get nothing when we just clean using IQRM. And we get some of them when we have very weak RFI. When using zero DM match filtering, it's also called Z dot, we get mostly everything back. in both the cases, whenever we use SKF and ZDMF. But you can see there's some kind of a pattern that all of these follows. That means whenever Z dot is applied, you're going to lose some of them, and it's very systematic. Just to evaluate, just to investigate what's happening, we try to do something on the second set of test vectors, which contain known RFI, just noise and pulse. So we cleaned that using ZDMF as well, and then we found something like this. So these are 4 different widths of the pulse, and then based on the widths that we have the fraction of recovered pulses again. So this effect of losing pulses was also discussed in the original paper that was that introduced 0 DM match filtering, and that happens due to subtraction of mean across the time samples. So any pulse that you pass it through ZDMF or 0 DM match filtering, you get these bars, which are like dips in the time series, and which also reduces the amplitude of the pulse. And this depends on the width of the pulse as well. More the width, more would be these dips, and then lesser would be the signal to noise ratio that you're going to get for the pulse. Hence, you'll start losing pulses. So yeah, when we did the same thing for even test vectors containing broadband RFI, we lost many pulses, and it was something similar. This is an observation. And for narrowband RFI, so we had test vectors that contain only narrowband RFI, and then which of different strengths, basically 2 sigma, 3 sigma, and half sigmas. And then when we cleaned them using SKF and IQRM, we had something like this as recovery. So the right side is IQRM and left side is SKF. So SKF consistently did not recover this 0.5 sigma pulse. And there was supposed to be some reason behind it. So the only difference between these both, in some sense, were the metrics that they were using. So we tried, and since IQRM has a capability of using any moment or metric that you give it to use, so we tried to clean the same test vectors using different metrics and force IQRM to use that kind of metric. So we use 3 metrics that's called ACF1, kurtosis, and skewness. So when we use ACF1, everything is clean, everything recovers back, because ACF is something called autocorrelation function with a single sample lag. That means you assume that 2 samples that has RFI are correlated in some sense, and noise is not. And if you use kurtosis, we still miss some of them, and skewness, we miss some of them. So the conclusion was, if the RFI is really faint, if the strength of RFI is really low, the skewness and kurtosis are not the best metrics to use, because they don't produce so much variability in the the baseband that tries to flag the RFI. So yeah, choosing a best spectral metric makes a huge difference. So what next? So we have new RFI algorithms coming up that are designed, and that needs to be tested. And also, we need to look at number of false positives coming out of these pipelines. The same technique can also be used for periodicity searches. We're just doing single pulse search right now, and also look at effect of baseline variations, because they might also affect the number of candidates coming out of both, even single pulse as well as periodicity search, and also evaluate how good algorithms are doing on them. And then in the era of machine learning, for single pulse searches, there are already a lot of techniques that are introduced. And maybe we can use this kind of test to cover all the corner cases that we want. So yeah, here is the conclusion. So we have developed this method and can be used to test any kind of post-correlation beamform data. And we have tested 3 algorithms, and IQRM and ZDMF seems to be the best one, given that we would still lose some pulses due to the effect of ZDMF. And yeah, thank you.
Thanks, Raghu. Questions for the speaker?
So I wanted to ask while injecting the pulses, what was the SNR range of the pulses? And does the RFI rejection, both the algorithms, how does they perform for the high SNR candidates?
Yeah, so the SNR we started to choose from right from 9 sigma till we went on till 182 sigmas. And the difference was not, there was actually no difference between any of them. So since we are flagging at the max till 25% of the bands, even the 9 sigma ones are detected back. And also, since 182 sigma seems to be a lot, but then when spread across 4096 channels, it still becomes less, and RFI algorithms do not flag them. So yeah.
So apart from the SNR, if you vary the DM and width also, so how does that matter there?
Yeah, so it's just trying to cover all the parameter space.
Yes.
So we have.
You said SNR didn't matter, but so though the width of the pulse or the DM matters in this?
No, I mean, I didn't say SNR didn't matter. So it means that SNR does matter because, ultimately you're detecting the pulse with some SNR and the pulse should not be vanished. But it's a 3D, it's not just 3D, it's like 7D parameter space that we try to cover. And then we had multiple, samplings of DM, width, and SNR. And these results that you see are across all of them. So the plots that you had were like for different widths and different DMs in x-axis, and then fraction of recovery in the y-axis. So it does take account into width and DM.
Really nice talk. I was wondering if you are thinking about extensions of your work to more realistic FRB, I guess like pulses and also pulse morphologies, and also I guess the RFI itself, like if you have data from, let's say, airplane RFI or something else that you could just inject over there.
Yeah, so the paper that we wanted to focus on, we willingly not used those real observation data because, as I said, we don't have control. At that point, we'll not have control over everything. Like we can't challengingly place the RFI where we want or such things like that. And also not have control over all the process that are happening, like, modulations of, and then also red noise, all of these things. So in order to test a pipeline, I think that's the best idea to use. We have observation data and then we inject pulse and cover like a 3D parameter space and do. Especially for what we wanted, we didn't think that was the ideal case to use. But yeah, definitely this can be used to do that.
Okay, let's stop there and thank Raghu again. Now I guess there's a coffee break, right?
Yeah, we come back at like 4:10.
4:10.